Good morning, everyone. Today it's my pleasure to have this chance to share our group research activity on nitrogen electrochemical reduction. So we will talk about our activity on nitrogen oxidation, reduction, and also some activity on urea synthesis by combining nitrogen species with carbon dioxide to form urea. So the nitrogen cycle in the world is a very important process for ecological system. They include many different ways of nitrogen fixation. There's a biological way, the atmosphere process, and means that the atmosphere with the electricity, we can do this. Currently in the industry, the majority of the nitrogen is produced by so-called ammonia was produced by Haber-Bosch process. And this ammonia will further be made into fertilizer, all kind of fertilizer. And so Haber-Bosch is a very important process. However, it's under so-called harsh condition. The temperature is high and the pressure is high. And this process, by estimation, will contribute to 1 to 2% of global annual energy consumption. Yes, and also they also consume account for like 2 to 3% of global CO2 emission. So if there's any innovation in this process, can reduce the energy consumption, CO2 emission in this nitrogen fixation or ammonia production process, that will be very useful. Professor Chen Jingguang from Columbia University, he presented a very interesting perspective or review paper. They showed that there are different ways can do the nitrogen fixation or nitrogen cycle process. One of them is the electrocatalysis. Okay, and in this process, he presented that nitrogen can go, oxidation process, reduction process, even between the, nitrogen oxide and nitrogen ammonia, they can also be directly converted to each other. The typical device for nitrogen electrochemical or electrocatalysis process for nitrogen conversion process is like this, mostly like, a cell. And on the anode side will be the OER process. If we're talking about nitrogen reduction, on the cathode side, there will be nitrogen be converted to ammonia. And this process is driven by electricity. Supposedly, this kind of electricity can be from renewable energy. Then that will be, sounds much more greener, this process. And you can do it at room temperature, ambient condition, no pressure. And of course, you can also do it for nitrogen oxidation reaction. In this case, the two will switch. The nitrogen will fit from this side and get a nitrogen oxide, nitrate, not as a gas state, will be stay in the solution. And this side will be HER process, hydrogen evolution process. So for the catalytic nitrogen reduction process, there are different, different mechanisms. So there could be so-called dissociative pathway, means that nitrogen first, the nitrogen molecular dissociate from each other, and then on the surface of catalyst started, reduction process. Or nitrogen can be one of the nitrogen molecular can be reduced first when both atom is on the surface of catalyst, or simultaneously both atom in the molecular can be reduced simultaneously. So this is called associated distal pathway, and this is called associative alternating pathway. Nitrogen reduction process has a few limitations. Of course, the current research in this area is a low efficiency and low yield. If you look at this kind of process map, you can realize that the majority of region is hydrogen evolution. So nitrogen reduction facing the challenge of competing reaction by the hydrogen evolution process. No matter you choose, alkaline, you choose a basic condition, Depends on different wattage range. The nitrogen reduction process is relatively limited range. So how to improve the further efficiency till now is still a big challenge. So many new concepts have been developed, including the catalyst design by doping or other process on the surface of the catalyst, also generated lattice strain, etc. On the other side, the people also thinking of a combined nitrogen reduction process or nitrogen fixation process with other activation processes such as the plasma. They also show a very promising result. This area is quite attractive recently, so the publication number also increased rapidly. And so for this, in our group, we want to start with one work on the nitrogen oxidation. The reason is that we started this area about 4 years ago. By that time, nitrogen fixation is already being many group has explored, and many new catalytic material have been reported, but nitrogen oxidation has not been well studied. So we want to pick up a new angle to jump into this area. The typical way for nitrogen oxidation will involve a few steps of reaction. Nitrogen go to the nitrogen radical, and finally all the way to the nitrogen oxide radical. After reaching this step, the rest one from nitrogen oxide radical to become a nitrate molecular, this one is not a rate determining step. Means that you might not require electrocatalytic process to drive this reaction, and or you might just spontaneously react with oxygen. So in how is it really react, we don't have a full conclusion, but in any case, you just consider this one is not a rate determining step. So it will be faster than this other reaction. And the reason we are interested in the nitrogen oxidation process, because in this proposed reaction on the cathode side is the ammonia generation, on the anode side is the oxygen evolution reaction. Ideally, you can replace this oxygen, then you have a full nitrogen chemistry, full nitrogen reaction chemistry. So that would be also an interesting cell. When you look at this reaction process map, so you can see that if you're doing it in the basic condition, the the potential for nitrogen oxidation will be lower. But for this case, you were facing the competition of OER reaction, oxygen evolution reaction. So in our case, we choose to do it in the neutral condition, while although the potential would be slightly higher, but we try to avoid as much as possible the OER competition. The first one we are started is try to set up a protocol in our process. The idea is that because nitrogen oxidation is a very low yield and a low efficiency process, you have to make sure that the product is really come from your reaction, not from contamination. So we have to do a lot of control experiment, try to determine where this nitrate molecular come from, whether it's only detect on the working electrode. Is this also in the counter electrode? And you have to do control the gas environment, the argon and the nitrogen, see whether, if let's say in argon environment, you also have the product, that means your process definitely have some problem, and a lot of purification process. So the first work for this one to us, the most valuable is the setup of this kind of protocol to make, to carry out in a correct way, to try to as much as possible to eliminate the possible error and the possible contamination from different process. Also, you have to do isotope labeled study. The first work we tried is using a palladium nanoparticle. The palladium nanoparticle do show certain Faraday efficiency, although not very high, 10% around, and the yield is also not very high. And the problem for this one is that we didn't choose a very good catalyst for nitrogen oxidation. The noble metal could be a good one for nitrogen reduction, but in case of oxidation, this noble metal may not be stable. They might go through certain oxidation process and become, 2+ or 3+ valent. Not here. Where's I will show that later. So that means our catalyst not so stable. Under the nitrogen oxidation process, there are certain oxidation happening to the palladium catalyst and make it the cycling performance is not so good. And so we did this Faraday efficiency and the yield test, and we used this isotope labeling and also many control experiments to see that the product really come from the reaction. Just now I mentioned this is the oxidation process on the palladium. Before it's a palladium 0 metallic structure, and after the process it become 2+ or 2+ ion. So that finally our cycling performance is not so good. And then later we did another try to use a titanium oxide as a support for this catalyst. We try to dope leucania inside the titanium and make the whole structure to be stable under the nitrogen oxidation process. And meanwhile, we doped the additional. We added additional leucania. This leucania become leucania oxide, which is distributed on the surface of titanium oxide. The idea here is that leucania doped into titanium oxide will become active center for the nitrogen oxidation. The actual leucania oxide will be a little bit that can help the the oxidation of the nitrogen, because the nitrogen oxidation process you do need a little bit oxidation species, and so this is some calculation to show that after doping the the titanium lattice shows some shift. This is phase diagram. You can see that with the titanium, the doping of the leucania should be not much, because based on the phase diagram, you could only dope the within 10%. Actually, what we get is really small amount of titanium. To this, if at the room temperature below this is 600 K, so below this temperature, the value could be even lower. If you keep on adding a little bit more leucania into this system, they can easily precipitate out as a leucania oxide. So in this case, the performance of this yield will be higher than the previous palladium catalyst, and the Faraday efficiency can go Faraday efficiency can go higher, and maybe in the next slide. Okay, so Faraday efficiency value. So this one, the doped leucania is a true active center for this reaction, because if you try to physically mix the leucania and titanium oxide together, you do not have enough yield. Only you dope leucania into titanium, you will get this significant enhance of the yield. And the idea is that the leucania itself is a good OER catalyst, but once it's doped to the titanium, it will inhibit the OER reaction process. Lastly, some people also looking into whether oxygen vacancy in the titanium itself can acting as active center for nitrogen oxidation. But right here we show that it's not much. The Faraday efficiency we can reach is about 25%, and we do that at all different current density. And lastly, we also use you know, the nitrogen 15 to check whether our reaction is fully from this reaction. By the way, here I have to emphasize that the nitrogen isotope itself had to be need to be careful, because the purity of the isotope you purchased, it could be an issue. You know, some of the isotope is not a very high purity. You might have a impurity itself. So before doing that, we have to check the quality and check the do necessary purification for the nitrogen 15 itself. I think I'm gonna skip this slide. The next one, after we set up the protocol in our lab for nitrogen fixation, we can start to also you know, jump a little bit into the nitrogen reduction, which is ammonia production process. In this process, we set up a new so-called new orbit called orbit connection with the nitrogen, which is called a pi back donation. This is similar like people using the boron catalyst. But here what we use is the bismuth based catalyst. And this one, when we try to for this molecular, when we try to take oxygen vacancy from this molecular, you'll generate this 2 unpaired electron. Once you attach another OH group on the surface, so we will make this particular bismuth become to have an empty orbit. So this bismuth will become the active center for nitrogen absorption, and later will activate the nitrogen you know, molecular to become a nitrogen radical and reduce the energy barrier, and finally improve the efficiency. So before that, we did a you know, a whole set of calculation, try to confirm that there are, you know, unpaired electron in this 3 different kind of catalysts, you know, pure bismuth oxygen iodide, or with oxygen vacancy, and with both oxygen vacancy and the OH group on the surface. And once we do the, you know, synchrotron the exact test, we show that with this as compared to the pure with oxygen vacancy and with both, you can see there's a difference in terms of bismuth oxygen the coordination, and there's some, you know, some variation to confirm the 3 different kind of structures. And this is the DFT calculation to try to say that these 2 bismuths are different. These 2 bismuths are different, means this refers to these 2 bismuths are different. So the one with the OH group attached will be the active center for this one, based on the, you know, the activation energy barrier calculation. And so the way to detect the nitrogen ammonia is by indolphino blue method and the ammonia electrode. Means we did 2 kind of detection process and compared the result. They are, you know, they are within a reasonable error range, so which to confirm our detection of this ammonia is reasonable. So the one we have for the both we did it in both neutral and acidic condition. The neutral one and the acidic condition both show a reasonably good Faraday efficiency and yield. However, later on we find out if you do it in the acidic condition, after this is in neutral, they also in the basic condition also good. In the neutral condition, during the cycling, this one performance still okay, but in the acidic condition, upon cycling, your yield will drop significantly. The reason is that after this kind of test, we find out the surface OH group will be, you know, the surface OH group will reduce. The idea that the surface OH group on the acidic condition is not stable. They can be, you know, detached as a water. So that will reduce, will, you know, change the surface state of this catalyst, and that will affect the binding of the nitrogen and reduce stability, reduce the efficiency. Yeah, that's the conclusion. So in this case, we try to say that both surface oxygen group and also the oxygen vacancy is important to tune the surface electronic structure to enhance the nitrogen reduction process. And last work, I want to talk a little bit as the electrocatalytic urea synthesis. So in this process, this work we work with Professor Yu Guihua and Professor Song Li and Professor Li Shuzhou. Shuzhou gave a presentation yesterday together. So we try to show that on the surface of Indian hydroxide, there's a proper coordination, actually 4 active sites together can allow the proper anchoring of a nitrate and the carbon dioxide. And this will promote the bridge, or we call it linkage, between the nitrogen and the carbon to form a carbon nitrogen bonding. Well, there's some work last year. There's a group shows that purely nitrogen also can react with carbon dioxide to form a urea, but the efficiency is still relatively low, about 9%. So here, if replaced with a nitrate, we can significantly enhance the efficiency to more than 50%. The nitrate, however, nitrate is not as a nitrogen as ideal reactant because you have to think how to get the nitrate. One way you can find the natural resource. There's some natural resource of nitrate. The other is that currently industrial wastewater have significant amount of nitrate in it. So if we can find a way to recycle those industrial wastewater and use as a reactant for this process, this could be useful. So for this process, we produce 2 kinds of catalysts. One is with a surface of 100 exposure. The other is with some mixture surface of 110 exposure. And this is just a calculation. For the 100 exposure that through this XRD and the observation, the cubic structure, they're showing a 100 zone axis. In case you want to introduce a little bit more 110 surface, through synthesis, you can get this. There's still 100 surface, but just some this 110 surface will introduce additional surface that affect your catalytic surface absorption. Here we want to show that the 100 is the primary active surface. 110 is not. So that's why this kind of catalyst shows a less conversion efficiency. And these 2 kinds of catalysts show similar, similar electro surface area. By doing the modeling DFT calculation, we realized that the key step right here is that the second step right here, the nitrogen and the carbon linkage is the key to determine the selectivity. To determine they will go to the urea synthesis rather than go to the nitrogen reduction process or carbon dioxide reduction process. And to do this, because this particular catalyst, they have a 4 active surface site of Indian, which is an active surface for the binding of nitrate and also carbon dioxide. Okay, and this 4 active site coordination with proper length that allow the nitrogen and carbon to form a linkage under this environment, and that is one of the important process to promote the carbon nitrogen bonding, and will promote this reaction toward this urea synthesis. So this is one of the important concept. And for this detection, we again use some colorimetric method to show, based on the intensity of the color. And so through the absorption, UV absorption process, we can determine the concentration of the urea. And the urea, if Faraday efficiency can go as high as around the 53%, and the yield also can go close to about 500 microgram per milligram per hour, and yes, so the one of the interesting studies that later on we did this for confirm the reaction for we've confirmed the source for both nitrogen and carbon. The slightly different in the in the 110, 100 and 110 exposed the catalyst. That because the through the DFT calculation, the 110 surface not so active. We confirmed the reaction source, the reaction nitrogen source by the isotope process. Confirm the nitrogen source. We also confirmed the carbon source. And later on, we find that one interesting story that to enhance the urea synthesis, to inhibit the surface so-called hydrogen evolution reaction, we find out for this indium hydroxide catalyst, they are n-type, intrinsically they are n-type semiconductor. Once the carbon dioxide absorbed on the surface of this catalyst, the carbon dioxide electron captured, so they can make the surface layer to be more sort of like a p-type layer if you based on the the MS measurement. And this kind of a structure is it's good for the inhibiting of the HER evolution process. Through our study, find out if we use a CO2 as a feeding stock, to do the reaction, or without CO2, the Faraday efficiency should different. And this by checking the product, we find out hydrogen product is different in the two cases. So this kind of catalyst, we propose that can inhibit the HER process. And this kind of process actually, this kind of a finding can be useful for those other reactions like nitrogen reduction, carbon dioxide reduction. If you do not want the HER as a competing reaction, you want to inhibit HER process in your reaction. This could be one of the strategies. This one I think I can skip because they talk about the indium oxide. With similar coordination, they can achieve a similar Faraday efficiency and the yield. So lastly, this just summary. For NOR, the efficiency is still quite low. Efficient and yield quite low. So for this process, it's really very challenging. And also the kind of publication or reported research work also quite limited. So still encourage other group to to look into new strategy to promote this process. And nitrogen reduction currently also suffer from a low Faraday efficiency. It can be obtained use other activated salt like nitrate, or can combine with plasma, is reported by other groups. So there are some good progress has been made in this nitrogen reduction process. Lastly, for urea synthesis, C-N coupling is one of the key steps to ensure you go to the right direction to improve the selectivity. And inhibit the HER is a very important concept to enhance the Faraday efficiency. Catalyst surface coordination is also important for the C-N coupling. So I would like to thank my group member, my collaborator, and founding sources. Thank you very much.
Thank you very much for presenting nice works on 3 different interesting electrochemical reactions. So let's take a few questions from the audience. Any question? Yeah, Professor O, go ahead.
Thank you for the very nice talk, interesting talk on very difficult subjects. I'm wondering that I have a question on the urea formation. So you're using indium oxide or indium hydroxide as a catalyst for reductive condition. So I'm wondering that, first of all, indium is known for CO2 catalyst to form formate. So I'm wondering if you have detect any formate formation. And the second question is, the second question is that indium, I think that should be reduced to metallic phase under high overpotential. So I just wondering, have you measured the valence state of indium oxide hydroxide after urea formation?
Yes, yes. So these are the good question. Actually, this question during the reviewer asked this kind of question, so we did this kind of control experiment. First of all, the indium reduction process, we do check that. So under this potential, the balance of indium hydroxide was not changed. We did a few repeating experiments. Be honest, we actually initially we expect we might see this kind of reduction. And for the purpose of this paper, be honest, if there's a reduction or not, it's fine. If there's a reduction, we should just report, yes, there's a reduction, and the reduced state should be the true cathode. But in this case, we did the experiment. We didn't find out the reduction process. And second one is that the carbon dioxide reduction, we also checked. It's very interesting. Carbon side, we don't see any other side product, but while in the nitrogen side, we do see a few different side products to affect the total final Coulombic efficiency. So we find out there's hydrazine, there's ammonia, there are hydrogen. But in the carbon dioxide, the product is quite limited. It's not formate formate product find out. Yes, it is something interesting. We will further explore it. Yeah.
Thank you.
Sure.